Hello, everyone, and welcome back to another edition of IAC 101. Today, we're going to delve further into the subject of steam, a very important process in heating technology for industry. Part one explored the background of steam and the basics of the boiler. We're now going to talk about what happens after you make steam, including the distribution system, typical end uses, and efficiency considerations. So let's start with how you're going to distribute it and what issues we should look for. Normally, when looking where steam exits a boiler, you'll see steam entering one or two headers. A header is a very big pipe off of which you tap smaller pipe to send steam where you need it. So in general, steam is delivered in parallel, and there can be a whole lot of smaller steam lines snaking their way through a plant, often out the door and into other buildings. Where time permits, it's almost always useful to trace them and see what their end uses are. Sometimes you track a steam line to nowhere, and those are good opportunities to figure out why. Pipes with live steam are hot, and those shutoffs should be much cooler. Now, if you don't shut off any steam lines to nowhere, you're going to be wasting energy. In some cases, we've recommended disconnecting a steam line because while no steam was present in the line, conduction through the steel was keeping the unnecessary piping hot. In many cases, a plant will require two different temperatures for two different types of processes. You really don't need two different boilers. What you typically do is make steam at a high pressure in a single boiler, which would be the high temperature. And then you go through what we call a pressure reduction valve, or PRV, to knock the pressure down for part of the steam so that the temperature goes down with it. These PRVs reduce the pressure by going through a constriction, and so the energy content is not lowered. You do, however, make a lot of entropy and reduce exergy for those of you just finishing a thermodynamics course. If you do have a lot of flow going to a second pressure, often you'll see people stick in an actual back pressure turbine. A back pressure turbine is a way of making electricity through that pressure drop. And in fact, these devices are common enough for companies that make these back pressure turbines build to an inventory. So you can just call them up and say, ship me one of those 50 kW units, something like that. Now, these steam distribution systems or steam pipes are hot, very hot. And therefore they require significant insulation for both safety reasons and for energy efficiency. This is why we spend a lot of our time looking at insulation during plant site visits. We're looking to see if it is complete, and we're looking to see if there's any damage to the insulation. As you can see in this picture here, we have white insulation with uninsulated valves connecting different parts. Although it is not commonplace yet, a removable insulating Velcro secured wrap can be added to valves and elbows and things of this nature. And so we can often look at a very small piece of uninsulated steam pipe and make a good recommendation about it. Finally, if you see insulation that is wet, you want to bring that to the attention of management right away, because wet insulation is worse than no insulation. What happens is that if you have a pipe that's maybe a few inches in diameter, and if you put on a couple more inches of wet insulation, water wicking out to the outer layers effectively creates a larger pipe. And a larger pipe means more surface area and therefore more heat transfer. Now, moving on to the discussion on the end uses of steam. There are three uses of steam primarily: heat, moisture, and motive power. A lot of the time, all you want out of the steam is heat. We need heating for space heating, especially in the Northeast. And additionally, steam heat is used throughout a process heating in a myriad of ways, such as with cooking and chemical processing. Dryers and reboilers and distilling towers use the heat from the steam as well. Here's an example of a radiator, which you may have seen in an old home, school, or municipal building. The idea was to bring steam into the hot part of the radiator, usually the top, And then as the liquid collected at the bottom, you have a steam trap that would allow the liquid to go back to the boiler. You do not see these that often anymore, but they work fairly well, except when they have leaks. And then there would be hissing, and that would be very annoying. Most homes or buildings are now heated with hot water as opposed to steam. You'd also find that there's a lot of clanging associated with metal expanding and contracting as you continuously turn it on and off as needed. Besides the heat, the moisture in the steam is often needed in manufacturing food products, in the making of cardboard boxes, as mentioned before, and certainly in cleaning and sterilizing. Chemical reformers, which are used to chemically generate hydrogen, which is then used in many petroleum refining processes, also uses the moisture content from the steam. Recognize that you're going to have more makeup water when you do this because you're consuming the steam in the process itself. In food processing, for example, the moisture can be used for the blanching of food. We scald vegetables in boiling water and immediately place them in an ice cold water bath to halt the cooking process. We can also use the moisture to rehydrate dried products, sterilize equipment, and steam places to provide sanitary conditions. Additionally, we have the potential of direct steam injection to warm without the use of a heat exchanger by simply injecting the water with the steam. Its only purpose is to heat, but we consume the steam through this process, which is known as sparging. It's a low pressure steam application, and we'd probably have a pressure reduction valve before the sparger so that we could limit the amount of flow going into whatever we're trying to heat with the steam. However, it's a very efficient way to get high temperature water. And while less common these days, using high pressure steam to power something is still around. I'm a big fan of steam engines, especially some of the new designs. In many cases, you'll find that these operate in places where you don't want to have electricity for safety reasons, and so you could simply have a steam powered engine. You can also find steam powered pumps even within a boiler system themselves, which serves to pressurize the feed water. Now, the last big part of a steam system is the condensate recovery. As the steam gives up its energy, it changes its phase back to water, but it's still hot and it is very clean. And so you never want to throw it away unless you have to. Therefore, there is a significant amount of effort going into recovering the condensate that comes from taking energy out of the steam system. Now, if the steam is used up in the process, as we have talked about in a couple of the applications, or if your plain condensate is discarded because it's not cost effective, it can simply be replaced with makeup water. But you're going to have a lot of water treatment and a lot of needed blowdown in your boiler. This is normally to be avoided or at least minimized. Remember, the condensate is already hot, thus you do not want to pay to have it heated up again. And it's already been treated, so you don't want to waste that money either. As a result, we need a device that can remove condensate from the steam pipe while leaving steam in that steam pipe and send the condensate back to the boiler. And this brings us to the idea of steam traps. Steam traps remove condensate from steam lines. That's their one and only job. Plants can have hundreds to thousands of steam traps throughout a big steam system. And depending on the application, there are several different types of steam traps that can be installed. It helps to remember that what they're trying to do. Inside a steam pipe, you have a mixture of water in steam form and some in liquid form. And you want to trap out the condensate and leave the steam. Normally, we can use two features of the condensate to design a device to allow it to separate from vapor. The condensate is going to be much heavier and also a little cooler than the steam, and you can take advantage of both of those. Listed here are some of the steam traps you may come across in a plant, such as balanced pressure traps, ball float steam traps, inverted bucket steam traps, and many more. There are just too many to go into full detail of each type during an introductory episode such as this. Maybe we'll just do an episode on steam traps later. One of the most common steam traps, which is a mechanical one, is called an inverted bucket. An inverted bucket steam trap uses the weight difference between liquid water and steam to open and close a valve. And you can tell that it's working by listening to it. As it opens and closes, it makes a distinct noise. Tack, 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 tack. Actually, probably even faster than that. So if you go to a steam trap and it's making this sound, you know that it's healthy. But if the steam trap is quiet, you know it's having trouble. Now, since plants can be noisy, often an ultrasonic sensing device can be used. You can point a wand or the sensor itself near the trap, and it can give you a great readout. Okay, so the condensate from these traps is generally collected and returned to a tank before being pressurized and put back into the boiler. Now, we want the stuff to be liquid in this condensate return system. However, if you have steam traps which have failed in an open position, they're now pushing steam into that condensate return system. And sadly, this is not rare and is not a good sign. So now, as we return condensate to the tank, if it cools a little bit, that's okay because we're getting farther away from the boiling point. It's normally still under pressure and can flow back to a condensate tank, even if that tank is a little bit above atmospheric pressure. If needed, we see an occasional pump or two around a plant to help push the condensate back. Now remember that we do not want to return condensate if it is contaminated in any way, or if the distance you have to push it is prohibitively long and it would not pay to return it. Sometimes you'll see a condensate return system not in use because it was tried and failed and they decided not to continue with it. Now here's a picture of the condensate return tank, which is the point where we collect all of the condensate coming back from around the plant. It's not a high pressure tank. It's usually maintained right at or a little above atmospheric. This is where we would add make-up water if needed. And you'll usually find it elevated up off the ground because the pumps, which live below it, have the advantage of some hydrostatic pressure on their intake before those pumps push the liquid now out to the boiler at the boiler pressure. Whatever the desired pressure is, let's say 300, 400 pounds, that's the pressure on the output of these feed water pumps. The condensate return tank also commonly acts as a deaerator as well. It's necessary to remove gases that end up in the liquid water from all sorts of metallurgical activity or leaks or things of this nature. Often you're going to have CO2 and some other gases such as oxygen and nitrogen that would like to get out of the water before it goes back into the boiler. And this is done in the condensate return tank because the water is hot and at relatively low pressure, so you have the maximum amount of outgases wanting to leave the liquid. Deaerators are important and often not well understood, so I'd like to discuss them in a little more detail. The deaerator, meaning typically the condensate return tank, removes dissolved gases from the feed water. Now, using a valve at the top, we allow those gases to escape. But we'll also have to lose a little bit of steam. So there'll always be a small amount of steam escaping from the top. If it's a small amount, it's fine. But if it is a large amount, you might want to think about what's going on. Most likely you are returning actual steam through your condensate return tank from the steam system itself. At one plant we visited, I was told that the steam plume coming from the condensate return tank was large enough to help you find the plant from the highway. When you exit on exit 10, look for the steam plume. And that obviously needed to be addressed. If you put a lot of steam back into your condensate return tank because of failed steam traps, you're going to have to find a way of getting rid of that steam or find a way to cool your condensate return tank and get the phase change to occur there. It's interesting that because you have hot water in there, you would like to have insulated condensate return tanks, meaning you're going to save that heat you already paid for. But when you have to condense some of that steam that got back in there that wasn't supposed to, you end up cooling the condensate return tank and removing any insulation so that you have enough liquid to put back into the boiler. So as we study condensate return tanks, we learn a little bit about the health of the system. Now I'd like to say a few things about the concept of steam balancing. This is where we try to do both a mass and energy balance on steam in the whole system. Energy is sometimes a little tough to do because you need temperatures everywhere. But for mass conservation, all you need is flow rate in a couple of places, which is usually easier to tackle. But this is one of the most fertile areas to point out to plants where they have trouble in a steam system, especially if it's low pressure. Low pressure steam, while it's not all that hot, is very expensive to make, and significant issues can usually be found. One plant we visited had an 80,000 pound per hour feed water leak that had gone undetected until a steam balance was put together. This plant unknowingly had significant energy losses due to this unseen leak, which could have been underground. Probably the best number that you can use to describe how well a steam system is working is calculating the percent of condensate return. And we're referring now generally to closed systems. You're going to lose some steam due to blowdown, others due to the deaerator, and you'll probably lose some due to the process and some liquid that comes out from some steam traps that may not return. All of that goes together to create a loss. And so you would need to know flow rates in various places to find all that. But the easiest way to do this is to look at how much makeup water is being used. That's the only flow rate measurement that you need, how much new water you're putting in per unit steam or per unit energy into your boiler. We'd love to see that number down below 15% for closed systems. And even if you're consuming steam in the process, you should trend the amount of condensate being returned so that you can see how much steam is being used in your process and see if it changes dramatically. This is a great application for the Internet of Things, where you can have devices which talk to the internet and would keep you informed about all this stuff. And we once did analyze a prison in the Northeast which had closed systems that lost so much due to problems that it had a condensate return rate of only 7%. And that should get everybody excited about opportunities. A very common activity when we're in a plant is to look out for any ways to recover waste heat. Waste heat being a loss from any system such as process heating, or in this case, steam. Recovery of even a little bit of this waste energy can be considered free, which makes it a no-brainer. But first recognize that the waste heat is sometimes unnecessary and maybe the result of poor steam operation, so you should look for that first. Another thing to consider is that the steam system can be either a source of waste heat or a utilizer of waste heat. You can collect waste heat from other places around the plant and use it to support your steam system. We also have to think about what makes good and bad in a heat exchanger. As mentioned in previous episodes, you can do liquid to liquid heat exchangers, gas to liquid, or gas to gas devices. And clearly, the denser the material, the smaller the heat exchanger can be in order to achieve the energy transfer you want. Referring back to our first steam episode, it was mentioned that one of the more common ways of using waste heat is with what we call a boiler stack economizer. This uses heat from the stack to heat the feed water of the boiler and therefore reduce the amount of energy needed to create the steam. Using an economizer can save an estimated 5 to 10% of the energy required for the steam. Although these devices are implemented regularly, we still come across many places where they're not being utilized, but it makes a good thing to look for and provides for very quick paybacks. On the flip side, we also see cases where we have waste heat boilers using waste heat from someplace else, such as a furnace or chemical reactions that release a lot of energy. And we hope to create low to medium pressure steam and use that steam in other parts of the plant. You're going to find out pretty quickly the level of sophistication of any plant steam system. Do not be shy about suggesting improvements in the area of training or getting some outside help. In many cases, a steam system that is not causing trouble is ignored and can be operated in a very conservative fashion, and you'll find that you can save costs by as much as 20% just by paying attention and operating it more efficiently. Plants may not have equipment locally to evaluate their steam systems, and often people using the steam are just not responsible for the making of it, and thus may waste it and not worry about it. And of course, you have management that is all about saving money and costs. One of the things I like to do is, if maintenance issues arrive and they're not getting addressed, suggest that they outsource maintenance. This can be very cost effective, especially if things are not getting done. This brings us back to the idea of having an outside maintenance contract to manage your steam system and your steam trap. They're usually the most poorly maintained part of the steam system. Places we find that you can have as many as 50% of your steam traps either failing open, thus leaking steam or leaking steam into your condensate return system, or failing closed, which then pushes liquid further down into your steam system. If they need encouragement, we suggest that these plants get an ultrasonic leak detector. As I said earlier, there's usually a tick, 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 and you'll have one of your maintenance guys go around and keep track of problematic steam traps that need to be replaced or maintained. Again, outsourcing is something a lot of plants implement as a way of staying ahead of routine maintenance on all of their steam traps. Finally, you want to look at the ancillary systems of a steam system and see if there's any energy to be saved there. You have pumps and fans on the combustion system, and as you look at them, there may be potential for savings. And remember that there are lots of steam resources online. Here are a few free ones. The Steam System Modeler tool by DOE is an excellent online calculator for you primarily, and it will provide quantitative information to your client in a very easy way. Okay, this brings us to the end of our segment on steam. We normally find many opportunities to save money and steam in our plant visits and encourage you to do the same. In our next video, we will look at motor systems and some of the techniques we use to find energy efficiency improvements in a plant. Okay, Mike Muller again. Thanks for joining us. See you next time.